Our next two colligative properties come as a pair because they are partners to each other when we look at phase changes. So let's think about phase changes for just a second here. What we have, if we think about temperature and phase change or phases, we know that we have a freezing point at some cooler temperature and we have a boiling point at some higher temperature. The other thing that we can correlate this with is pressure. And so if we have solid over here and liquid and gas, the solid is not very affected by pressure. And liquids are not very compressible either, so these are not very affected by pressure, except when we start looking at our liquid to gas phase transition. So if we look at evaporation here, what we have to have in order to do this phase change, or boiling, if we are actually going very actively through it, is that in order to boil, the vapor pressure must equal the atmospheric pressure. So let's think about what that means for a second here. We just talked about Raoult's law, and we said that we have this liquid, and if we have a closed container here, a certain amount of vapor from that pure liquid will evaporate into that space that's there. So now if we think about this as an open container here and we look at boiling, we know from watching water boiling that we get these bubbles to form and then they rise up, and we don't really see much that happens after that. And what's happening during boiling is that you get these pockets of the gas form of whatever your liquid was. So let's talk about if this was water. Then you get pockets of water vapor. It does not break down. You know that occasionally we will have students with the misconception that when we boil, something breaks down the water into hydrogen gas and oxygen gas, and that is not the case. Boiling is a physical process, not a chemical process. And all phase changes do not chemically change their materials. So it's just water that's liquid being turned into water that's gas. It's the same compound, and if you condense it again, it returns to being exactly its water, liquid water. So these pockets of water vapor rise up and they boil out of the liquid. This can't happen until the vapor pressure, so that's the vapor pressure of the water, which is the water, or so it's this pressure pushing out of the liquid, right? And we know that the atmospheric pressure is pushing down on the liquid and keeping the gaseous particles inside that liquid. And so when your vapor pressure is now pushing with an equal force as the atmospheric pressure, now your liquid can fully boil, and that is what's necessary in order for boiling to take place. So remember, Raoult's law told us that our vapor pressure of a solution is less than the vapor pressure of that pure solvent. So let's think for a second. Okay, let's back up again. The solution, that means we have stuff dissolved in the solvent. And this is the pure solvent. All right, so let's draw ourselves a little picture. Here's our solution. We've got stuff dissolved into it. Here's our solvent. And we said our vapor pressure is less. Maybe that's extreme. Okay, there we go. This is our vapor pressure now. This is our vapor pressure over the pure solvent. So our vapor pressure here is higher than our vapor pressure now. So if we think about our solution, in order to boil, we need Pvap to equal P atmospheric. Since Pvap, our vapor pressure, is less than what it was for our pure solvent, that means that we're probably going to end up having to heat our sample up higher in order to get our vapor pressure high enough that it equals our atmospheric pressure, right? Let's think about that. So let's just think in millimeters of mercury, and I'm going to make up some numbers. Let's say that our atmospheric pressure is exactly 760 millimeters of mercury, atmospheric pressure, right? So let's say that our initial vapor pressure here for the pure solvent is 76 millimeters of mercury. So that's 1/10 of our initial, of our atmospheric pressure. And now let's say that in our solution, our vapor pressure has been reduced to only 70 millimeters of mercury. So here's our threshold, 760 millimeters of mercury, that we need to reach. And this is our pressure scale, right? And our pure solvent is right here at 76, and our solution is down here at 70. So they both have to get up to 760 millimeters of mercury in order to boil. This solution has a longer way to go, and so that means that the colligative property that we're going to talk about right now is an increase in a boiling point. Let me just write this as a complete sentence here. Our second colligative property is boiling point elevation. It's often abbreviated BPE. So boiling point elevation, we have this increase in our boiling point that is due to the decrease in the vapor pressure of our solution because we have dissolved stuff in our solution. Our calculations for doing boiling point elevation are pretty straightforward. What we're going to do is we're going to calculate a change in the temperature, and we're going to call this delta TB. And this is equal to the new boiling point minus the initial boiling point and it's going to be equal to the molality of the solution times the boiling point elevation constant. And that's what this KB is. It's called the boiling point elevation constant. And as you probably would expect, our molality of the solution, that has units of moles per kilogram, and our boiling point elevation constant has units of degrees Celsius over molality. And so that means that our overall unit is going to be in Celsius degrees or Kelvin degrees. Really, it's the same because remember that the change of temperature in degrees C is equal to the change of temperature in Kelvin degrees because these have the same size gradation between degrees. Okay? If you need a review of that, then head back over to the video where we talk about that. That video was the heat flow and heat capacity video, in case you need a reminder. The boiling point elevation constants are available in tables. These are not numbers that you would just know, and they're not numbers that are easy to just come up with. They're numbers that you would figure out through experimentation. So if we go and look at our table in the book, we can see what some of these values are. Table 11.5 in our textbook shows us some boiling point elevation constants right here, KB, and also some freezing point constants, which we'll get to in our next video. So for right now, let's just take a look at our boiling point. These are the ones for the pure solvent, and the boiling point elevation constants for these 4 liquids. So we have 4 liquids: water, benzene, which is an organic compound, ethanol, and carbon tetrachloride, another really common organic solvent. So these boiling point elevation constants are pretty variable, right? Water's is the smallest at 0.52 degrees C per mole, and then carbon tetrachloride is the highest at 5.02 degrees C per mole. So if you need a boiling point elevation constant, you just need to look it up in a table. So let's go ahead and practice a calculation figuring out how much our elevation, or how much our boiling point is elevated for a scenario. All right, so let's go ahead and look at a scenario where we dissolve 25 grams of sucrose, that's table sugar, in 100 grams of water. Or in 100 grams of ethanol, just for comparison's sake. And we will ask, what are the new boiling points? Okay, so we need to have the molality of each of our solutions, and they're going to have the same molality, right? Because we have the same mass of the solvent. So we need to figure out how many moles of sucrose we have. So sucrose has the chemical formula C12H22O11. So go ahead and pause the video and calculate the molality, or excuse me, the moles of sucrose first, and then the molality of the solution, which, just as a reminder, is moles of solute, that would be sucrose, divided by kilograms of solvent, which would be water or ethanol. Okay, pause the video and go give those a try. All right, welcome back. So for your moles of sucrose, you should have gotten 0.0730 moles. I found that the molecular weight of the sucrose was 342.300. What just happened there? Let's fix that. And so with 25 grams, this should be our moles. And we have 3 significant digits from our original number. We're using multiplication and division rules. So that means that we have our molality, which is 0.0730 moles divided by 0.1000. That's 4 significant digits, kilograms of water or ethanol. And so we get 0.730 mole for that solution. All right, so for water, our next step is we're going to calculate the change in the boiling point. So we have our molality, 0.730 mole, and we have our boiling point elevation constant, which for water is 0.52 degrees C per mole. So you can see that this is a pretty small number, 0.038 degrees C. Our new boiling point for water would only be 0.038 degrees higher. You probably wouldn't even notice it. Having increased significantly in temperature, unless you had a super precise thermometer. So let's look at the ethanol. Our boiling point elevation for the ethanol, this has a slightly higher boiling point elevation constant, but you can see that it's still pretty small. So we're not going to end up with a big change. So it's 0.0891 degrees C. And our new boiling point, and I just used the boiling points from the tables, right? So I know that the boiling point of water in Celsius degrees is 100 degrees Celsius exactly. And the boiling point of ethanol was 78 degrees. So our new boiling, 78.4 degrees. Our new boiling point is 78.489 degrees. So about 78.5 degrees C. And this, as I said, was 78.4 degrees C. So again, this is not a huge change that you would notice a lot in terms of this increase in the boiling point. And we're going to see that in some situations, our boiling point will be more affected depending on what we are dissolving, because it's based totally on how many particles we are dissolving, right? And so if we have a more concentrated solution of something, then that's going to definitely increase how much the temperature is going to change. So our factors for increasing the boiling point depend on the molality. So obviously the more concentrated something is, and on that boiling point elevation constant, which depends on the solvent. So the other thing that you need to remember is that we're always increasing the boiling point. So whatever value we calculate for this delta TB, that is the number that we're going to add to the existing boiling point to raise it. Okay, so in our next video, we're going to talk about freezing point elevation constants and some additional factors for solutions.